Welcome everyone. Today I'll walk you through eddy current testing or ET, one of the most powerful NDT methods used in industrial inspection. Principles, applications, and inspection guidelines based on API 577 and ASME Section 5. We'll cover how it works, where and when it's applied, and the rules that guide its use. Please be informed, this summary is intended to simplify the content based on the presenter's interpretation. Eddy current testing general overview, definition. Electromagnetic or eddy current testing is a non-destructive technique that uses electromagnetic induction to detect flaws in conductive materials, such as cracks, corrosion, or variations in thickness. How eddy current testing works. A coil energized with an alternating current generates an oscillating magnetic field that induces eddy currents in the test material. Eddy current testing detection principle. Flaws or changes in the material properties disrupt the flow of these eddy currents, which are then monitored by a probe. Eddy current testing expected output. The resulting changes in the eddy current's phase and amplitude are displayed on a screen, providing immediate feedback for technicians to identify potential defects in surfaces and near surfaces. What's included in the image? Number 1 is coil and magnetic field, how the alternating current generates a magnetic field. Number 2 is eddy currents in material, flow pattern in the conductive material. Number 3 is defect interaction, how cracks disturb eddy currents. Number 4 is probe types, absolute, differential, and reflection probes. And number 5 is signal response, typical impedance plane diagrams for lift-off, cracks, and material changes. How eddy current testing works. Step 1 is magnetic field generation. An eddy current probe, containing a coil of wire, is energized with an alternating current. Step 2 is induction of eddy currents. This alternating current creates an oscillating magnetic field that extends into a nearby conductive material. Step 3 is eddy current flow. The changing magnetic field induces circular electrical currents, known as eddy currents, within the material. Step 4 is flaw detection. Discontinuities like cracks, corrosion, or variations in material thickness disrupt the normal flow of these eddy currents. Step 5 is measurement and analysis. These disruptions cause changes in the eddy current's phase and amplitude. A secondary coil in the probe, or the primary coil itself, measures these changes. Step 6 is defect identification. The observed changes in the measured current indicate the presence of flaws, which are then displayed for analysis. Eddy current testing key applications. ET is a versatile inspection technique used across many industries. Applications include, number 1 is crack detection, identifying surface and near-surface cracks in metal components like turbine blades, fasteners, and welds. Number 2 is corrosion detection, detecting and quantifying corrosion or material loss in aircraft skins, pipelines, and heat exchanger tubes. Number 3 is material thickness measurement, measuring the thickness of metal and of non-conductive coatings, such as paint on metal surfaces. Number 4 is material sorting, differentiating materials based on their electrical conductivity, which helps confirm heat treatment or identify different alloys. And number 5 is bolt hole inspection. Specialized probes are used to detect cracks and defects within bolt holes, a critical application in the aerospace industry. Example of eddy current testing applications. For eddy current testing applied to surface crack detection, recommended probes or tools is pencil or pancake probes. Frequency range is between 100 kHz through few MHz. Its capability is to detect cracks as small as up to 0.1 mm deep. Differential probes for automation. Flaw orientation matters. For eddy current testing applied to non-ferrous metal sorting, recommended probes or tools is absolute probes or conductivity meter. Frequency range is not applicable, it using conductivity based. Its capability is to check alloy or heat treatment. Conductivity overlap use as indication only. For eddy current testing applied to subsurface crack detection, recommended probes or tools is low-frequency probes. Frequency range is low frequency. Its capability is penetration up to 10 mm. It is working to detect hidden cracks in second or third layers, thinning in multi-layer structures. For eddy current testing applied to heat exchanger tube testing, recommended probes or tools is bobbin ID probes. Frequency range is up to 600 kHz. its capability is, high-speed scan, up to 1 meter per second, detect wall loss more or less to 5%, dual or multi-frequency for support plate suppression, not for ferrous tubes. For eddy current testing applied to inline steel tube inspection, recommended probes or tools is encircling coils, frequency range is low frequency plus DC bias, its capability is, magnetic saturation reduces permeability, tubes up to 170 mm, weld zones tested with sector coils. For eddy current testing applied to ferrous weld inspection, recommended probes or tools is special weld scan probes, frequency range is typically 100 kHz through 1 MHz, its capability is, works through paint or coatings or underwater to detect cracks up to 1 mm deep times 6 mm long. Probe types and their uses. Probe type number 1 is, absolute probe. It is a single coil measures impedance change. Typically, used for general flaw detection, conductivity checks. Probe type number 2 is, differential probe. It is a two coils compare signals, difference output. Typically, used for detecting small cracks, minimizing lift-off effect. Probe type number 3 is, reflection probe. It is a one coil excites, another senses response. Typically, used for tubing inspection, heat exchanger tubes. Probe type number 4 is, pencil probe. It is a small diameter for tight spaces. Typically, used for bolt holes, small surface areas. Probe type number 5 is, encircling probe. It is a surrounds the test object. Typically, used for rods, wires, and tubing inspection. Probe type number 6 is, bobbin or tubing probe. It is an internal coil set, TX or RX or differential. Typically, used for heat exchanger tubes, detects wall thinning and axial/circumferential flaws. Probe type number 7 is, rotating bolt hole probe. It is a small coil rotates inside fastener holes. Typically, used for detects corner cracks and hidden flaws under fastener heads. Signal response interpretation in eddy current testing. Eddy current instruments typically display responses on an impedance plane diagram, XY plot. The signal changes based on the type of variation in the material. Number 1 is, lift-off effect, in this diagram labeled with purple color, cause, change in probe to surface distance, such as due to coating or probe tilt. Signal, a movement along a specific direction, usually downward or at an angle, on the impedance plane. Interpretation, indicates probe positioning issues, not a defect. Typical display responses. Number 2 is, crack or defect, in this diagram labeled with red and/or orange loops color. Cause, disruption of eddy current flow by a crack or void. Signal, a sharp deviation from the lift-off line, often forming an elliptical or loop pattern. Interpretation, the size and orientation of the loop can indicate defect depth and length. Typical display responses. Number 3 is, material property change, in this diagram labeled as green baseline shift with green color. Cause, variations in conductivity or permeability, for example heat treatment differences. Signal, a shift in the baseline position on the impedance plane. Interpretation, used for material sorting or detecting hardness variations. Impedance plane, labeled signals. How to read this diagrams. Axis, horizontal is for differential resistance or real, vertical is for differential reactance or image. This is the classic complex impedance display on most ET instruments. Lift-off line impedance plane, in this diagram labeled with purple color. It shows the direction your trace moves as probe to surface distance increases or decreases. In practice, the exact angle depends on test frequency and instrument phase rotation. Typically phase the display so lift-off aligns to a convenient reference axis. Crack indications impedance plane, in this diagram labeled with red and/or orange loops color. Surface breaking crack, smaller, distinct loop at a characteristic phase. Deeper or longer crack, loop grows and its phase often shifts, compared to shallow. Loop shape or phase vary with depth, orientation, and frequency. Material or heat treatment changes impedance plane, in this diagram labeled as green baseline shift with green color. Conductivity upward direction, often linked to hardness downward direction in non-ferromagnetics, produces a baseline shift along a relatively consistent direction. In ferromagnetic materials, permeability can dominate and rotate this vector, always verify with standards. Edge or geometry affects impedance plane, in this diagram labeled with cyan color. Edges, steps, and corners can produce strong vectors. Differential probes help attenuate these. For operational tip, use known reference standards, lift-off shim, notches or FBHs, conductivity blocks, to set phase so that lift-off and defect vectors are well separated for your specific frequency. Eddy current testing acceptance criteria. Number 1 is ASME Boiler and Pressure Vessel Code, ASME Section 5, Article 8. It covers eddy current examination requirements, calibration, procedure, personnel qualification. Important, ASME 5 provides the method, but acceptance criteria come from the referencing code, for example ASME Section 8 for pressure vessels, B31.3 for piping. Typically, no indication exceeding the reference standard signal. Acceptance criteria number 2 is provided in the following ASTM standards: ASTM E243 for copper and copper alloy tubes, ASTM E426 for austenitic stainless steel tubes, ASTM E571 and E690 for nickel alloy tubes and in-situ testing, ASTM E309 for steel tubes with magnetic saturation, ASTM E215 for aluminum alloy tubes, ASTM E2884 for eddy current testing with sensor arrays. All of these standards above define calibration reference standards and reject levels, such as drilled holes, EDM. Notches. Common rule: reject any indication greater than and equal to reference standard signal unless proven irrelevant. Acceptance criteria number 3 is provided in the API codes, API 510 for pressure vessels and API 570 for piping. Both these API codes refer to ASME 5 for method. Acceptance is based on fitness for service and remaining life calculations, not fixed amplitude limits. Eddy current testing is often used as a screening tool, with UT or other methods for confirmation, and acceptance criteria number 4 is provided in the product specifications, for tubing such as SA-249, SA-213. Acceptance criteria often come from ASTM A1016 or the product specification. For example, reject if signal exceeds that from a drilled hole, e.g., 0.031 in/0.8 mm, or notch of 12.5% wall depth. The advantages of eddy current testing. Number 1 is non-contact. The test probe does not need to physically touch the material, allowing for inspection of hot, delicate, or underwater surfaces. Number 2 is high sensitivity. Eddy current testing can detect very small, hairline cracks and defects that other NDT methods might miss. Number 3 is minimal surface preparation. Most testing can be performed on coated or painted surfaces, saving time and cost. Number 4 is high inspection speed. With advancements like eddy current arrays or ECA, large areas can be inspected quickly in a single pass. And number 5 is portable equipment. Most instruments are lightweight and portable, making them suitable for on-site inspections. And the limitation of eddy current testing. Number 1 is limited to conductive materials. The method only works on electrically conductive materials and cannot be used on plastics, ceramics, or other nonmetals. Number 2 is limited depth of penetration. Eddy current density is highest at the surface and decreases with depth. This limits the detection of deep subsurface defects. Number 3 is highly sensitive to material properties. Changes in material conductivity or magnetic permeability can interfere with readings and require careful calibration. Number 4 is sensitivity to surface conditions. Surface roughness, scale, and other surface imperfections can produce unwanted noise or false readings. And number 5 is orientation sensitivity. The method is not effective at detecting flaws that run parallel to the direction of the eddy current flow. Advanced eddy current testing or ET methods address some of the limitations of conventional testing. Number 1 is eddy current array or ECA, uses multiple coils in a single probe to scan a larger area in one pass, providing C-scan images for easier data interpretation and faster inspections. Number 2 is pulsed eddy current or PC. Uses a pulsed magnetic field to penetrate thicker materials and inspect through insulation and non-conductive coatings, making it ideal for detecting corrosion in pipelines and storage tanks. Number 3 is remote field eddy current testing or RFECT, primarily used for inspecting ferromagnetic tubing. It is sensitive to general wall loss and more effective than conventional ECT for thicker carbon steel pipes. Thank you.